As Richard had mentioned, today I'm going to talk about how to assess and prevent high cycle fatigue failure. I'm going to walk through a discussion talking about why fatigue is important, what is fatigue, what actually factors affect fatigue life, take a brief historical view to see how much has changed and how much hasn't changed in the last 150 years, and then look at design philosophies for fatigue, and then how we can incorporate fatigue life curves and use them to go off and predict fatigue, both in the high cycle, low cycle regime. And then end up looking at a overall fatigue design process that can be adapted and used to go in and virtually predict fatigue. So the question comes up is, why is fatigue important? And if one looks at most parts today, they tend to be well designed for things such as static failure, highest loads that we plan to see, meaning that most of them will fail either through fatigue or wear out. In a Battelle study many years back, they found that 80% of the failures on parts were due to fatigue, and the cost was very high. The key aspect is even applying some of the simple design philosophy for a design against fatigue would remove a large portion of those. Historically, the way that we've designed for fatigue is we just made the part stronger. But in an era where we have to deal with lightweighting, that no longer is a valid design approach. And as you see at the bottom, it basically says that if you over-design your part, the part won't really perform in the marketplace. And again, the engineers who do that again will not as well. So what is fatigue? Looking at several dictionary definitions, it comes off as basically a weakness in the metal that's caused by repeated variations of stress. And repeated variations of stress is the key aspect here. Again, it says a weakness due to a series of stresses. The aspect here is that repeated stress cycles, even at relatively low levels, can cause fatigue cracks to start and to grow. And so the last part here is more what's actually happening, and that is that these repeated cycles of stress initiate and can grow a crack. Now, we'll see that this initiation portion is very, very statistical. But fatigue cracks are caused by cyclic loading, not time at stress, but changes in stress. Even if the stresses aren't that large compared to our static criteria, yield, UTS, we still can see failure. And in many cases, a crack can initiate and eventually grow to failure. Trying here to differentiate between the two modes of failure. The first one we're all pretty familiar with, where we're going to look at our component, we're going to look at maximum possible loads. You can see in here, we're going to design it for stiffness, for static strength. So we're taking our largest possible load and going in and comparing it against yield, comparing it against UTS. Second mode of failure, fatigue, looking at cycles of stress at load levels substantially less than we're interested in terms of static failure. But over time, repeated applications of those cycles can cause the part to initiate and get cracks.
Okay, so you're at least a couple of slides back. This one, yeah, we lost you midway through this one.
Okay. I apologize for that. Looking at the two modes of failure, one can see if I were to test for static properties, monotonic properties like tensile strength or yield, I would see that in multiple tests, I'd end up with very, very similar results. The scatter is very, very small. When I test for fatigue life, that's not the case. We see that there is a very large scatter in the results. And the reason for that is due to the fact that the initiation portion is growing through the microstructure, which changes from specimen to specimen. Because of this, we tend to break the fatigue life into two different sections. One we call crack initiation, the other we call crack growth. Truthfully, they're both crack growth modes, but the crack initiation portion is growing through the microstructure, and hence we will see different performance between part to part because of that, because each microstructure is unique. We cannot actually do crack growth at that regime without knowing what the microstructure is. So here we use empirical approaches to try to mimic it. Once the crack gets large enough, we call that crack growth. And now the crack is large enough that is independent of microstructure, and we can actually predict that reliably with numerical approaches. To kind of emphasize that, if we go off and look at our test specimen and look at basically in detail where we start to grow the crack, we initiate a crack in a single grain, and basically that crack grows through the grain till it hits the grain boundary. Now, if it has enough energy and the grain on the other side of that boundary has a similar weak direction, in a similar direction, it can actually break through the boundary and start to continue to grow through the second grain, and hence the third grain. After a few of these grains that have failed, the crack length gets large enough that its driving force will overcome this microstructure. It no longer sees the microstructure, and now we kind of go into what we call a stage 2 crack. It stops growing in basically a shear direction, starts to grow in a maximum tension direction, and now it's growing through a material that for all purposes now is homogeneous isotropic, things that we can go off and predict. The actual crack growth is dependent on many things. The primary driver for a fatigue cycle is its size. It's basically the difference between the max and min stress in that cycle. Other factors do come into play though. The mean stress or the average stress of that cycle is also a contributor to the fatigue. If the mean stress is tensile, it causes more damage than if the mean stress was compressive. There's a variety of things about the geometry and the loading that are important. Things such as the type of stress concentrations in the part, the type of loading that's causing the stress, whether it's tension versus bending versus rotating bending, the actual size of the part. And the reason for that can actually be seen somewhat down below where I have two shafts in bending, one much larger diameter than the other, and they both have the same surface max stress. But because the upper shaft, the larger diameter shaft, has got that larger diameter, we see a larger volume of it is under the high stress. Again, what we're doing is stressing the microstructure of the part. So anything that stresses a larger physical volume is going to cause possibly more fatigue damage or basically initiate damage. And that has to do with stress concentration factors. A larger stress concentration factor has a larger area of stress. If I move from loading, instead of bending in this case to tension, instead of having just high stress at the top and bottom of my shaft, I have the same stress across the entire shaft. There's more volume to basically initiate a spot. Again, size of part. If I have a large part, there's more places there to possibly have highly stressed grains that have a preferred weak direction to grow the crack. Other things could cause changes in the fatigue performance as well. The surface finish. If I have a rough surface on my part, that roughness can be actually initiation points for fatigue cracks. Temperature can change the fatigue performance. The same way that elevating temperature could decrease the monotonic properties, it also can decrease the fatigue properties. And residual stresses, either due to manufacturing process, to overloads. Again, anything that leaves a stress that changes the mean stress can again influence the fatigue life. Just a look historically at this, we recognized fatigue really on the dawn of the industrial age. The moment they started making things all the same, and some failed and some didn't, there was basically a push to investigate what was going on. And early on, people recognized that it was the cycles of loading going in, and hence named that failure mode fatigue. There were very early on fairly sophisticated measurement and fatigue curve creation to go off and do design. So in the 1800s, there were techniques to go off and improve the fatigue performance. The militaries in Europe were going off and using autofrotage to basically leave residual stresses in gun barrels in the 1800s. Wohler went off and designed basically tests and a fatigue design curve to design railroad axles. But it wasn't until the 1900s that they even knew what was causing the physics of fatigue. So all this was possible just looking empirically at what behavior was, not knowing what was physically causing it. The next 50, 60 years, there's improvements in terms of understanding the physics of fatigue, the influence and ratio of things like mean stress to life, or ways to go off and characterize the curves they're going to use for fatigue damage into equations, looking at stress strain behavior, looking at ways to incrementally look at fatigue damage and how it accumulates. But the next major change in how we dealt with fatigue really comes into the 60s and 70s, where we start to have available compute power. The moment that we can go in and numerically start to represent these things, because these operations are cycle by cycle, they're very numerically computation intensive. The real advance in the last 30, 40 years has been really putting these onto the computer. So the innovations of development of finite element simulations to virtually go off and predict stresses, and then taking that information into computer-based fatigue prediction, has really been the advancement. Over time, there's been a variety of design philosophies to go off and design for fatigue. The first one, and actually the one that's still prevalent today, is called Safe Life. In here, we're actually looking, in most cases, where parts are driven by initiation rather than crack propagation. And we go in, design a part with a factor of safety, hence that we try to capture the population of that part and have a life that's going to, a predicted life that will go off and serve either the life of the part or use that predicted life to come up with a replacement schedule. But this is done looking solely at the loads, no inspections of the parts. This is easily applied to mass-produced parts of relatively low cost. second approach that was developed to try to improve on safe life was called fail-safe. And here, what they're looking to do is make a fatigue failure be non-catastrophic, such that there was always, if there was a part that failed, there was a redundant load path in the component. Obviously, this isn't applicable on many components where it's very difficult to have two load paths, though you see it a lot in civil engineering structures today. This was done initially aerospace, and it was deemed not to be sufficient for aerospace applications, and hence we have a third design philosophy called damage tolerance. Damage tolerance takes the attitude that somewhere in my part I already have a flaw. I have a crack or an inclusion of a size that I can't find, but it's there, and it's sitting in the worst possible location. And so damage tolerance takes that initial flaw and goes cycle by cycle, growing the crack until it reaches some predetermined critical length, and then looks at the number of cycles it takes to do that, and uses that to set maintenance schedules to go off for complete non-destructive investigations of the part looking for cracks. Now, this requires different design philosophies in terms of materials. One, they tend to use materials here that are quite tough, that basically are relatively insensitive to fractures. They design in things like crack stops, but it requires a routine maintenance to go in and inspect the entire aircraft or component. And so it really is only applicable to really high value assets. So the majority of the parts that we see today are still safe life in general. Now, going back to that historical diagram, it showed that in the 1860s, a German engineer, Wöhler, did a fairly intensive study of his railroad axles. He actually measured the real loads in operation of these axles. So axles on the train was turned into load transducers to actually measure the loads that were going into the axles. He then developed a test rig that would actually rotate the axles loaded and go through and test his individual axles at the real loads they were seeing, and he was able to design basically a fatigue curve that he could use to predict life. Now, again, remembering what I had said, at this point in time, no one really had a clear understanding what the physics of failure were. But just looking at the relationship, the empirical relationship between load cycles and fatigue life, they were able to go off and create the fatigue curves and do design. His real emphasis here was looking at the fatigue curve where it goes horizontal on the bottom right-hand side. What he saw with constant amplitude loading, at some load level, he never saw failures beyond less than that load level. So it was a stress level or a load level on his part that he was able to control to guarantee he had infinite life. Jump ahead 150 some years, and what we do today is we create test specimens of materials, and we put them in a test rig under either load application or displacement application cycles, and we count cycles to something that we deem to be failure, whether it's breaking the specimen or a load drop off or a visible crack. And we take all that test data and we put it on a plot and we fit a curve to it. Sounds familiar, doesn't it? So the way that we're dealing with the crack initiation portion of fatigue isn't substantially different than Wöhler was 150 years ago. The differences come in here that Wöhler tested an axle. His curve was his physical axle, so that curve had baked into it not only the fact that it was ductile iron, but it had the geometry, the stress risers ahead, the surface finish, any residual stresses. What we do today primarily is test materials. So we go off and we make identical specimens of our material, and we test these as close to perfect specimens as possible to failure. Now, the curves that we create here talk about the actual alloy itself, but are missing other things that would be in our parts. Things like possibly the mean stresses, the residual stresses, the surface finish. So all this additional information, we go in and we tack onto the performance of our material curve to go off and try to make that curve simulate our part. And you'll see the curves that we create actually have many, many different formats. What I have here are just 4 different examples of fatigue curves that you run into. The 2 on the left-hand side, the upper one is just a standard stress life curve. And many times we see that if we take the stress life data and we plot it on a log-log or semi-log graph, we end up with a straight line or close to a straight line. And engineers like straight lines because it's easy to characterize the equation. Down below that, we have, again, a single curve, but here it's going into a relatively complex polynomial, trying to capture the low cycle and the infinite cycle regime, as well as the standard portion between 1,000 and 1,000,000 cycles. Again, fatigue life is not only sensitive to the size of the cycle, but most times to the mean of the cycle. So on the right-hand side, we have curves that are going in and actually measuring not only the cycle size, but the effect of the mean as well. At the top, we have just a family of SN curves, each one at a different mean stress level. So again, what I could do is once I have the cycle size, I could also go off and look at the mean stress of that cycle and choose the appropriate curve or interpolate between them. Down below, we actually have taken a totally different track to describe the cycles, where above the vertical axis was the stress cycle size, and the horizontal axis was the number of cycles to a predicted failure. The bottom curve here is actually the horizontal and vertical axis are a stress state. So the horizontal axis is the mean stress of the cycle. The vertical axis is the stress amplitude, or the size of the cycle. And each one of those curves represents a constant life, meaning if I followed the red curve, it's describing the stress state that would be for 10 million cycles. The blue curve for 100,000 cycles. And so these are called Hague diagrams or constant life diagrams. I believe that you will find so many different ways to describe these fatigue curves is because the early calculations were really reading off a curve. And so people would generate curves that were in the conditions that they were measuring or analyzing their components. So the vertical axis of stress might be amplitude, range, max, whatever was the easiest for them to predict. Those curves are created and can be used in different regimes of loading. And so the simplest curve that we run into, we call stress life, and here we're using a linear stress value that we measure or predict off our part. And the fact that it's a linear stress, we can only use that in places where the loading and the stresses are proportional. The driver for fatigue is really strain cycles. And The only time that stress and strain are proportional when we stay below the yield stress. So a stress life approach is really only appropriate out in what we consider to be the high cycle regime. And here the high cycle regime is material dependent. So we look at what load level causes plasticity, any appreciable plasticity, and then what life that would be. And that kind of dictates the lower bounds of my stress life curve that I can use. So that transition region they're showing there actually was a point where they say they start to induce plasticity in the component. So anything below that really shouldn't be used with a stress life approach. If I take that same data I could look at that data instead of cycles of elastic stress. I could look at that in terms of cycles of elastoplastic strain. Now I'm actually looking at a measure that I can use not only in the high cycle regime, but in the low cycle where I start to see plasticity. Elastoplastic strain is a good measure where I'm looking at areas where I have yielded the component. And so using elastoplastic strains, we can go in and actually predict life in the low cycle regime, but the high cycle regime of the strain life curve mimics stress life, so it's actually applicable in both places. The downside to strain life is it's computationally intensive. I need to have some way to predict plastic strains, either a nonlinear FE analysis or corrections on the loading. The curve itself now is not nearly as easy to interpolate. And so strain life is very difficult to do by hand. One reason we tend to migrate to stress life whenever we can. The last piece of this is going off and looking at how we, once we have that data, how do we do design with it? And again, looking at safe life, we tend to be looking for a way to measure stress levels that give us some measure of factor of safety. And we could be doing this either with single cycles, going off and evaluating the largest load on my structure and using that to calculate a factor of safety. And we can actually do that calculation at different levels of precision. The first level we show there is actually going off and trying to measure the stress cycle against some parameter that was estimated from monotonic properties. If I open my handbook from Shigley, there's sections in there that would give me estimates of things like fatigue limit based on things such as material UTS. I go one step more detail, take the approach that Wohler did, and actually generate these stress life curves. Now I actually have a physical curve that I can go off and pick the stress level that is the fatigue limit and use that in my design. Those factors of safety could be brought into calculations that not only look at the stress level, but the mean stress. So the third approach here, I'm going to one of those Hague diagrams that not only includes the size of the cycle, but the mean stress impact as well, and using that as my calculation. And then finally, what one can do is go in and look at the load histories cycle by cycle and start to accumulate damage and come up with a predicted life through the entire load history as the most precise approach. So we have a fatigue curve that we've created, and again, this curve really hasn't changed a lot in 150 years, and the way initially it was used was as the design guide itself. I have the curve here on a horizontal axis. I have the stress range, the size of the cycle that I'm applying this to. The horizontal axis is life to a specified failure. All I do is take the stress range, in this case, the difference between the min and max stress of my cycle, and I put it on the vertical axis, and I move over until I hit the curve and drop down, and it tells me how many cycles of that size can I endure before I break. So my 300 megapascal range is giving me a 3 million cycle life. Again, this is nothing more than the back of an envelope calculation that I can do. The downside is I can really only do this on simplified loadings. Another way to look at this is to go in and say, I have my 300 megapascal cycle, I come over and I come down, and now think about what that really means for a single cycle. It took 300 million cycles to break the part. So I could imagine that that one cycle uses up 1 over 300 million of the life. So taking the inverse of the number of cycles, that quantity we call damage. And damage is really how much of the life we've basically taken away from applying that stress cycle. This becomes crucial downstream once we start looking at realistic loads. To do fatigue, we have to go off and characterize what our part sees over its life. And that could be basically estimated with something as simple as I have a constant amplitude loading, I assume I see it this many times. The way that we would approximate this early on is find the largest load my part's ever going to see and make that load last for the lifetime of the part. Obviously, that's going to severely over-design the part, but again, that was my best procedure. I could take the real loads on my part and then basically decompose them into blocks of constant amplitude. So I have different size cycles, maybe different means. And a collection of these blocks of cycles is a much better representation of the overall loading the component can see. Now, it can be tested on a fairly simple test rig. It could also be analyzed with a little more work, but still analyzed by hand. The real life scenario where I have my variable amplitude loading, I have loads changing over time, basically it's computationally too difficult to go off and do by hand. This basically now forces us to go in and use the procedures that were kind of developed over the last 100-some years in terms of characterizing cycles with rainflow counting, coming up with ways to go in and accumulate damage cycle by cycle, looking at the arena of plasticity in the overall fatigue calculation. So this chart here shows a procedure for calculating a single location life from real measured history. So I start out with a measured stress history or a predicted stress history. And one of the things with fatigue, we only really care about when the stresses change direction, when they reverse direction. So the first thing we do with that measured stress history is we go in and we throw away everything but the peaks and valleys. We don't care how we got from this valley to that peak. We just care that we got there. And then once I have that history of peaks and valleys, we have to go in and characterize cycles for that. The approach that was developed in the 60s by Endo is called rainflow counting, and today it's the most reliable way to go off and look at a variable time history and pull cycles out of that represent the cycles that are going to cause fatigue. And so going through a rainflow count, I can break down my histories into point pairs of peaks and valleys and characterize them in a list, characterize them in a matrix where I have the size, the mean, and the number of counts for each one of those. I take all those cycles and I can process them through our fatigue curve that we saw earlier. Again, each cycle has a cycle size that I could easily go off and figure out what the number of cycles to failure are. Again, the inverse of that is incremental damage. I could add on to that additional calculations that would deal with things like mean stress. And so what I end up with now is for every cycle that was in my history, I can calculate the damage, how much life it has used up. And if I sum up all those damages, they tell me the total damage on the part. The inverse of that damage is life in terms of repeats of my time history. So I have a way to go off and take a complex load history and actually analyze it. But again, this isn't something really on the back of the envelope. This is now is in the realm of numerical computing. We take this now and we think about our entire part and the process we want to go through. Today, we work in a virtual environment for design where I start out with a CAD model that has my part geometry already defined. I bring that CAD model into Workbench, and in Workbench, I perform numerical analyses that look at its performance. And again, these could be quasi-static, they can be dynamic, but I'm generating stress or strain states that represent the different loadings in my history. I can then bring those into ANSYS Design Life, where I take the stresses from the FE, from the virtual model, I then pair them up with measured or estimated load histories and put together stress histories just like we had as a starting point on the previous slide. And from that, be able to go off and predict fatigue life for every component of my part, or every test location of my part, node by node, element by element. And here in this virtual calculation, we can go off and quantify whether we're going to hit the fatigue targets we expect with our design. If we don't, we go back in and reanalyze, basically redesign the part and reanalyze. And we go through this sequence until we come up with a design that looks like I can put it on a test and it won't break immediately, it won't live forever, but it's going to kind of sit into that regime where I have my target life that I'm trying to design for. At that point, we end up going off and usually building that component and testing it. Here on this chart is showing that we build a physical prototype, which is a bad thing in terms of fatigue testing, because among the other things that affect fatigue performance, the manufacturing of the component does as well. And so going off and building a prototype, not following exactly the same manufacturing procedures that the final product is going to use, may not capture all the fatigue performance, good or bad. And again, this is a kind of repeating cycle. One of the things that's very difficult to do is take all these unknowns in terms of fatigue and go off and do the fatigue prediction first time around. Many times we see that we go through several iterations of comparing predictions to test data to go off and refine our predictions. There's so many things that affect the fatigue life. We need some guidance in how each one is affecting the overall performance of the part. And so this is kind of a growth pattern here where this procedure is something you build into your design procedure and use it over time. The key here is we're doing much of the design for fatigue up front, and that's critical because fatigue tests are expensive. I actually have to have a part to test. They can also be extremely long. Think about this. I have to go off and use the loading that my part's going to see over its entire lifetime. Those tests may run weeks or months. And putting that long duration test in sequence with a design process just stretches out the design. So the goal here is to go through a lot of the initial design virtually the same way we use FE to go off and do static criteria. And then once we feel comfortable, go off and put that into a test. And those procedures that exactly exist today inside of ANSYS Workbench. You can go off and Workbench, drag in mechanical systems that will go off and predict the performance requirements, stresses from different styles of physics, be it transient, quasi-static. We take that information, import that into a system from mechanical that is an ENCODE design life system that can go off and do stress life or can do strain life, so low cycle or low cycle and high cycle fatigue. And internal to that system, we bring in measured histories, fatigue properties in terms of those fatigue curves, and are able to go off and very efficiently calculate life across the entire component. So in summary, I apologize for the delay there. Fatigue life is important in terms of us coming up with a proper design. Fatigue life is all crack growth, but it's in two regimes. One, basically initiation, one, propagation. Here we're looking primarily at initiation, which is really kind of dominates a safe life calculation. There's lots of factors that influence the fatigue life in that initiation phase in terms of size of cycles, mean stress of cycles, size of parts. Using the information that we can get from physical tests, we can go off and calculate fatigue life estimates, and some of them can be done as simply as a hand calc. If I have a simple loading on a part in the high cycle regime, it's nothing more than looking at the fatigue curve and going off and doing a single calculation. However, we can start to incorporate virtual fatigue simulations by using virtual models, virtual stress analysis using leveraging finite element calculations inside of a fatigue prediction, and here be able to go off and accommodate actual loading histories, the lifetime of a wind power system, or a life of an aircraft, total life of a car. We can do this in both high cycle and low cycle fatigue, because the moment we go to a numerical calculation, the calculation high cycle to low cycle follows the same basic procedure. The computer's now doing it, so it's easy. We can get life estimates across the entire model. And what this gives us is a more precise estimate of fatigue life. And the more precise we can get on the estimate of fatigue life means the closer to an optimal design we can get.